All right, so putting everything that we talked about in the last couple videos together, now we're ready to talk about the first law of thermodynamics. But before we can do so, there's one more term I've got to introduce, and that is something called a state function. Now, a state function says this. These are properties that are determined by the state of a system. Irregardless of how that state was achieved. Okay, so what properties are we talking about? So the state functions that we're talking about, these are temperature, pressure, volume, and energy. So these are state functions. So what I'm saying is that a state function doesn't care about how you got to that beginning point. It doesn't care what's going on. All it cares about is where you started with and the final. So that's it. It just only cares about where, your starting point, your ending point. Doesn't matter what's going on in the middle, just as long as you start at one point and you have a finish. So let me show you what this means. Let's say you and I are going on a hike, and we start at the same location at the bottom of the hill. Now, there's two different ways of going up this hill. You decide, well, you know what? I'm going to go pretty much the more direct route and just start climbing up. Okay. Meanwhile, I decide, you know what? I have this really nice path over here. It's pretty. The slope isn't as bad. It's pretty scenic. I'm going to go the red path. Okay. Now, which one gets up to the mountain faster? The blue path, because it's more direct. Which one takes a longer time? The one on the red, my path. Now, what I'm saying about a state function is it doesn't matter which path you take. It doesn't matter if I took the blue path or I took the red path. All it matters is that here's where you started and here's where you finished. And that's what a state function does. It only cares about the initial and it only cares about the final. Doesn't care about what happens in the middle. Doesn't care about that. Okay? Now, all that being said, let's talk about the first law of thermodynamics. So the first law of thermodynamics says this. It says that energy cannot be created nor destroyed. It can only be converted from one form to another. In other words, this sounds really familiar, and it should be, because that's the law of conservation of energy. So the law of conservation of energy is essentially the first law of thermodynamics. Now, this is pretty difficult to prove, but because you have to, in order to prove this, you have to measure the final energy value, you have to measure the initial energy value. So it's very difficult to get that. But if we were to get the final energy values and get the initial energy value, what we could measure, though, is the change in energy, okay, delta. And so this delta E thing, this is a much easier thing for us to measure. So we're not going to be able to measure the final and the initial energy values, but we can for sure measure the change in energy, and that's what we're going for. Now, this delta E thing that we're talking about, delta E is really the internal energy. Okay. Now, some textbooks may refer to internal energy instead of writing delta E. Sometimes you may see it as delta U. Okay, and that's totally fine. That's the same thing. right? I'm just trying to use delta E because, yeah, delta E is energy. That makes more sense. All right. All right, now the internal energy of the system has two components to it. So you have the kinetic energy component, and then you also have the potential energy component. Kinetic energy deals with the molecular and the electron movement, while the potential energy deals with attractions and repulsions. Okay, so you have those two different forms. Now, it is impossible to calculate the total energy of the system, but that's why we calculate the changes in energy. It's a lot easier to do that. So going back to the Hindenburg for a minute, if we know it's exothermic, how do we show that? Use the first law of thermodynamics. If this is your reaction here, 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water, then the way that we would you prove this using the first law of thermodynamics is to say that delta E is going to be the internal energy of the products minus the internal energy of the reactants. Or in other words, delta E would be equal to the energy content of 2 moles of water minus the energy content of 2 moles of hydrogen plus 1 mole of oxygen. Okay. Now, since this reaction gives off heat, the energy of the product is less than the energy of the reactants, so this reaction has to be exothermic. So if we were to apply the first law, we could say this, that the change in energy, internal energy of the system, plus the change in internal energy of the surroundings has to be equal to 0. So that's what the first law of thermodynamics is saying, that the change in internal energy plus the change in energy of the surroundings has to be equal to 0 because you can't create nor destroy energy. So that means that the total change, the change in internal energy of the system is going to be equal to the negative delta E change in internal energy of the surroundings. Okay. Now that's all well and good, but a more useful way of writing this is to write the first law in this equation, that the change in internal energy, delta E, is going to be equal to Q plus W, where, again, delta E, that's internal energy. Q is going to be represented as heat, and W is going to be represented as work. So now the question is, how do we represent Q and W and show that this is going to be exothermic, endothermic, all that good stuff? So exothermic and endothermic can actually be answered with the Q term. So if Q ends up being positive, we know that this is going to be endothermic. So it's absorbing energy. And if Q is negative, then it's exothermic. All right, so those two are the easy ones. It's the work part that it gets a little troubling. So if work ends up being a positive value, that means that work is being done on the system. And if work is negative, that means work is being done by the system. All right, so for us, what we would prefer is W to be negative, because that means that whatever our system is, it's doing the work for us. So ideally, we want W to be negative, because that means the system's doing the work. If W is positive, that means we have to do the work. So that's how we interpret Q and W for this reaction. Now, Q is heat. We're going to talk about heat quite a bit in the second half of the chapter, and actually in the next video as well. Let's talk about work, though. So work can actually be defined in physics as the force of an object multiplied by the distance that the object travels, or work is equal to force times distance. W equals FD. Now, how do we look at this in terms of a piston moving? Okay, so here's our piston. And so we've got this piston and it's pushing, we've got this plunger that's being pushed down. So there's a force that's being applied to it. Okay. All right. So eventually, at some point, if this is a car piston and the piston is pushed down, that means that gas is going through. There's an explosion. The piston pushes up. And so here's what we see in the second part. The piston goes up, but the same pressure is still being applied. So the pressure hasn't changed. It's just this change in the volume that's being applied. Now, eventually, that gas, when it gets pushed through the piston, that piston still goes down. So that way it ends up going back to this first picture. Okay. All right. So when the piston goes up, like it's like what we're seeing in the second picture, what this is talking about is that it's doing, you may see this as PV work, or this is known as expansion work. Okay, so in light of this, we can actually define work from a chemical point of view, because a reaction is not going to move. It shouldn't be moving down the hallway. So we have to define work in terms of chemistry, in terms of pressures and volumes. So for us, we define work as work being equal to negative P delta V. Okay, where pressure, P is pressure, and this is measured in atmospheres. V is volume, and this is measured in liters. So the unit that we get should be, the answer should be in liter atmospheres. Now, liter atmospheres doesn't mean a whole lot to us. But what we can do is take this unit and convert it to a unit that does make sense, and that's joules. So we define that 101.3 joules is equal to 1 liter atmosphere, and that's the unit that we use to define work. Okay, now what about heat? Now that we talked about work, let's talk about heat. Heat is not a state function, so just like work, neither of these are state functions. But the sum of heat and work gives rise to a state function. So while heat on its own and work on its own are not state functions, when you add them together, that does give you a state function. All right. Now, that being said, let's try one problem out before we go. All right, so here's a problem. A gas expands and does PV work on the surroundings that's equal to 279 joules. At the same time, it absorbs 216 joules of heat from the surroundings. What is the change in energy of the system? So we know this equation. The first law of thermodynamics says that delta E is equal to Q plus W. All right. Now we just got to figure out what these numbers are. So you know you got one number that's 279. You got one number that's 216. Okay. Let's go after the easy one first. So heat, Q, is going to be 216. And because it's using the word absorbed, we already know that Q has to be positive. Okay. So Q is going to be a positive 216 joules. So we can put that in. 216 joules. All right. Now here's where it gets a little tricky. It's saying that it does PV work on the surroundings. On the surroundings. So the work is being done on the surroundings equal to 279 joules. So does that mean that the work's being done by the system on the surroundings? It actually says that the work is being done by the system on the surroundings. So this has to be a negative. Okay, so work should be a negative 279 joules. So if you take 216 joules plus a minus 279 joules, because we know that number should be negative, that should give you a negative 63 joules overall.